So we've got a really interesting lesson ahead of us today. We're going to be analyzing and building electrical circuits today. Now, of course, obviously we're just going to be doing it through diagrams, but we will be getting to something a little bit more interesting next week where we're going to apply the information we learned today in a pretty unique way. Anyway, let's get started. So we're going to learn about how electrical circuits are designed today. We're going to look at the symbols used in circuit diagrams. So in other words, when you make like a blueprint sort of thing for an electrical circuit, we're going to talk about the symbols that they use in that. We're going to be analyzing electrical circuits to figure out what they would be doing if they existed. We're going to talk about something called a series circuit as well as something called a parallel circuit. And then we're going to finish off with a very quick discussion on microcircuits. There's not going to be a lot that you need to know on that one. Most of it's those first 4 chunks today. Let's get going. So circuit drawings right off the bat. When planning out an electrical circuit, engineers and electricians will draw a circuit diagram planning what the circuit will look like. These are often called schematics. Right? So a schematic is basically just like a blueprint plan of what your circuit is going to look like. Now these diagrams use special symbols to represent different parts of a circuit. Generally there are 3 or 4 main components. These exist in all circuit diagrams, of course. There's an electrical source, which is either a cell or a battery. Remember the difference between a cell and a battery. A cell, of course, is only one block, whereas a battery is a bunch of cells that are stuck together. Anyway, just so you know, that will be important again today. There's a conductor for electricity to flow through, in other words, a wire. That's kind of obvious. There's a load, or in other words, a device, to turn the electrical energy into some other form of energy. This could be a light bulb, this could be a household appliance, it could be anything that actually is using the electricity. And then last but not least, and again, this one doesn't always show up, but it's still very, very important, is a switch to control the flow of electricity. So in other words, something to turn it on and off, right? Those are the 4 main components. You don't always have a switch. Sometimes you only have these 3. But a switch, of course, is still a very critical part of a circuit. Now, this, straight out of your textbook, these are all the symbols that can be used for different things in a circuit. You might actually want to pause the video here and like give it a read through, but I'll go through the ones that are really important. The first one, of course, is a conductor. It's literally just a line, right? So the lines, of course, show the wire, right? And a conductor conducts electricity through a circuit, not a big surprise. Now, a cell is where things get a little bit more complicated. And this is the one where you got to really look carefully on it. A cell is basically a break in the circuit line where there are perpendicular lines that are parallel to each other, right? So it's perpendicular to your conductor, but parallel to one another. One of the lines is longer than the other. The longer line, or the large bar as they call it, is the positive end of your cell, right? Because remember, a cell has a positive end and a negative end. So the bigger line is positive and the smaller line is negative. Now the next one is a battery, which is a very similar picture, appropriately so, because remember, a battery is just a bunch of cells stuck together. Notice on this one, you got a large bar and then a small bar, and then a large bar and then a small bar. What that's really saying is, it's like there are 2 cells stuck together. So this is a battery that contains 2 different cells all in one. So remember, a battery is just a combination of cells. That's important to understand, that a battery is just a bunch of cells stuck together. Really important. Next up, a lamp. A lamp, of course, basically just looks like, well, kind of like the little inner part of a light bulb, right? The little twindly, like, piece of tungsten in there or whatever, right? Usually I just draw it as a circle and then like a squiggly line, right? It doesn't have to look exactly like this, just something similar to that so we can understand what you're actually doing, right? Now, the lamp, of course, could be any other load as well, generally speaking, but again, lamp is usually with the little symbol there. Anyway, so a resistor, on the other hand, is one of my favorite ones, actually, because it's quite appropriately drawn. It's basically just where your line starts getting all jagged, right? So in other words, remember, resistance ups the resistance in that conductor at that point, and that's kind of appropriate, right? It's like you're hitting like a bumpy road or something. So it controls the amount of current in a circuit. That's the whole purpose of a resistor. You're not going to see too many of those, but still important to know. A switch is a very clear one. It's basically where your line gets like these 2 dotted points on it, and then like a bar. And generally speaking, we'll draw it as like an open switch, even if it isn't open, right? You just draw it that way so it's very clear that there's an open switch there. Next up, these ones are very uncommon. An ammeter, right? So in other words, something that's measuring the current, or a voltmeter, something that's measuring volts. You won't really need to worry about those ones too often. A rheostat is kind of like a resistor, but then there's like this weird arrow to it. You're not going to have to worry about that one too much. A motor, you might have to worry about this one. It's basically where there's a circle with a couple dots inside of it. Okay, that tells you that there's a motor, and remember, what a motor does is it converts electricity into mechanical energy. So it's actually getting something to move. Instead of thinking of it as mechanical energy, you could also think of it as kinetic energy. Kinetic means moving. but it's just a matter of perspective there. And then the last one, a fuse. It's kind of like a switch in terms of its appearance, but there's like a little squiggly line here. And in case you're not aware what a fuse does, it's like a safety measure. If the current in that circuit gets too high, this piece is designed to melt before your conductor does, so that this piece will melt as soon as it's starting to get into a bad point, which breaks the whole circuit, and then electricity would no longer flow and it's no longer dangerous, right? That's the whole idea of a fuse. You won't have to draw that one very often, though, don't worry. All right, so we're going to draw a circuit here. I would appreciate if you pause the video and give this one a try on your own. I'll read this first, though. Draw a complete circuit that contains a 3-cell battery, a light bulb, a switch, and a resistor. Okay, so I want to see if you can do this, and remember, it needs to be a complete circuit. So in other words, it has to actually work. Many different ways you could draw this. Give it a try, though, and then I'll show you how I would do this. Okay, so what I'll do now is I'll draw this, this circuit. Remember, you could put this in whatever order you want. And it has to be complete, but let's see how it goes. First things first, just because it's the most complicated piece on this, I'm going to draw my 3-cell battery. 3-cell battery is just 3 cells stuck together. So I'll do my positive, negative, positive, negative, positive, negative. There's 3 cells there, and then I'll connect it with my lines to get my circuit going, okay? So there's my 3-cell battery. That's ready to go. Now we also need to have a light bulb, a switch, and a resistor. So I'm going to take my conductor here. Ooh, that looks not great. There we go. There we go. I'm going to take my conductor. I'm going to go this way. I'm going to put my light bulb here next. Now, a light bulb, of course, another word for that is lamp. So I usually just draw a circle, and then I get like a squiggly line. And now I'm going to draw this sideways, but that's all right. Get my squiggly line going. It's going to be something like that. Okay. That's good enough. Kind of turn your head to the right. You can kind of see that that's the idea. It doesn't have to be a work of art. You just have to have an understanding of the fact that that's a lamp, right? All right, now I'm going to continue drawing my conductor. So I've got the battery, I've got the light bulb. Now I need a switch and a resistor. It doesn't really matter what order we draw this in, at least in this question, it didn't tell us, so we can just draw them in however order we want. I'm going to put my switch over here. A switch is where you do like a little point, and then another point a certain distance away. And then we usually draw it as open. And again, you can draw that line on either one. You can draw it here, you can draw it there. It really doesn't matter. I'll draw it over here because why not? There's my switch. Now, yes, we draw it as an open switch, even if it is a full circuit, at least for now. Some people do draw them as like closed and stuff because that does represent the circuit's complete and all that. But of course, when you have a switch here, it's not the end of the world. You can literally just close a switch and now you have a complete circuit. So if you drew it as a closed switch where it literally just looked like something like this, that's okay, right? Not the end of the world. Anyway, I'll erase that. We are good with our switch. Now let's get a resistor in there. I'll do it on the side, coming up here. And then remember, like I said before, resistor is my favorite one. It's like a jagged line. So yoink, 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 yoink. That was awful, but you know what? I'll do that again. Yoink, 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 yoink. There you go. Good enough, right? So it just has to be a jagged piece there, just so we can tell. That's a pretty basic drawing. That's nothing special. But again, that would fit the bill for being a totally appropriate answer for this. Anyway, moving on. All right, circuit analysis. This one I took out of your textbook, and I think it's honestly a little bit advanced for where we're at right now, but I think it's interesting to talk about at very least. This picture right here is a circuit diagram for a remote-controlled toy car that has lights on it. Let's analyze the circuit diagram. If you want to analyze this one on your own, you can pause the video here and try to figure it out. But I will explain to the best of my ability what's going on here. So first things first, we notice that this one is to get the car going forward, and this one is to get the car going backwards. Well, why would the same circuit be used to get the car to go forward and backwards, and how would it work that way? Well, let's analyze this real quick. First things first, we have a battery, a 2-cell battery, as a matter of fact, right here in the center. Now, analyzing the forward one, you can see that the positive end of our battery goes across this way via a switch that kind of like directed the flow of the circuit this way. And then it went all the way around to this piece right here, which is actually a motor, which is also connected to a light bulb. So when the motor is running, when there's power going through the motor, there's a light bulb that's actually attached off of this. So in other words, if you were to press the button on the remote for this car to get this to start going, of course, as the motor's going, the lights on the car would also turn on, right? Because there'd be electricity flowing through both of them. Anyway, so they've drawn it so that going forward, we have the positive end going this way. Now, just so you know, of course, electricity really flows from the negative to the positive, okay? Because that's the way the electrons are really going. So if we look at the negative end, our electrons are going this way through this switch piece here, and then up this way, flowing through this whole system, and then back down around. Now, again, the electricity flowing this way when it's going forward. When it was going backward, however, notice that the switches are aligned this way now, and the negative end is going this way. So the electricity is actually flowing this way through the motor. Well, how motors can work is if you reverse the way that the electricity is flowing through it, the motor will opposite in an opposite direction, or operate, sorry, in an opposite direction, right? And in terms of going forward or backwards, the way that your tires are spinning, which is connected to the motor, would influence whether the car is going forward or backwards, right? So this is kind of an interesting way of doing this. This is a very advanced diagram for where we're at right now, but it is still kind of cool to look at. And it's also worthwhile to note that they drew the switches closed, which again is fine. Drawing it closed at least makes it very clear where the electricity would be flowing, but if you want to draw them as open, that's fine as well. It really doesn't matter that much, at least not to me. All right, so series circuits. This is the next thing we're going to talk about. And I quite like these because I think they're kind of silly, but they do have uses, right? So anyway, there are different types of circuits based on their design. The simplest type of circuit, easiest one to understand, is called a series circuit. Now, a series circuit is where all the loads occur on one path for the electrical current, okay? So all of the loads are like chained together in one path. Now, here's what the interesting thing about this is. If one of those loads in the circuit breaks, like let's say the loads are all light bulbs and one of the light bulb breaks, then the entire circuit gets knocked out because there's no complete circuit anymore. If a load is broken, that often means that the connection from one end of the load to the next end of the load is broken as well, so the electricity will not flow. Another thing to note about this is each additional load added to the circuit actually increases the resistance of the circuit. It makes it harder for the electricity to be pushed through it, and therefore that would decrease the current, because remember, if you increase your resistance, you're decreasing your current. That's from Ohm's law. Can't forget about Ohm's law. Now, a light switch in your home is part of a series circuit. This is why if you turn your light switch on, your light bulb comes on, but if you break that switch down, the light bulb goes off, right? Now, the light switch, of course, is connected to a power supply in your house, which isn't on a series circuit. We'll talk about that a little bit later, but your light switch is a series circuit because it's just one thing connected in one line. If you had a light switch in your house that operated like a whole bunch of lights, and then maybe that could also be a series circuit. Usually, actually not. Usually they'll do them in a bit of a different way so that if one light bulb goes out, you're fine. But still, one light switch in your house, generally speaking, is part of a series circuit. So again, a series circuit is just one path for the current that's going to pass through all of the loads, okay? Now, here's the interesting thing about series circuits, of course. Some Christmas lights, especially older Christmas lights, are infamously wired as a series circuit. What that meant was if one of your light bulbs on your Christmas lights went out, then all of the bulbs would go out. And you would have no idea of knowing which bulb went out unless you literally checked every single one to see if they were actually still intact, right? So the reason that they wired them this way was it was a lot cheaper and easier for companies to do that, right? So it'd be easier just to put them all in series and just say, hey, we'll line it up all one line, just going through all the light bulbs, and that's fine. And to be totally fair to series circuits, sometimes it's fine to have that. There's sometimes no problem with having a series circuit. The Christmas lights are not one of those times. You should not have a series circuit on a Christmas light. That's insane. So if you've ever seen, as you can see in this picture here, from the movie National Lampoon's Christmas Vacation, there's one part, of course, where they're getting their Christmas lights out, and the dad, of course, says, hey, you know what, hey, Russ, that's the name of the kid. He's like, come on, unravel these. You have to check every bulb, just by the way, right? So in other words, because they're all broken, or the whole light strand isn't going to work, not to mention they're knotted up, of course, they don't know which light is broken. So you have to check every single bulb. And it took a long time to do that. It was a big pain. Nowadays, of course, most Christmas lights you buy aren't wired in series. Some of them I would imagine are, though. Like if you bought a cheaper strand of Christmas lights, they probably still would be. But anyway, moving on. All right, so the other type of circuit that we have to look at are parallel circuits. This kind of solves the problem of the series circuit. What a parallel circuit does is each load has its own path for electricity to flow. What's nice about this is if one of the loads goes out, the other loads are still going to be able to operate because they'll still have a path for electricity to flow. So for instance, I'll just look at this picture right here just because it's important to analyze how this works. Let's say that this first light bulb went out, totally broke, right? Smashed to pieces, that whole link is broken. Well, notice electricity is still going to flow from your negative end of your battery. That's a 2-cell battery, by the way. It's going to flow from the negative end of your battery. And yeah, it can't get through this gap here, but the electricity is still going to find a way to go through this way, and it's going to find a way through this way, right? So it has all these pathways to eventually get to your positive end. Uh, this one being out doesn't affect these other two, right? It's totally fine that this one is out. The electricity can still go through them. Now, of course, oops, let me erase that. Of course, if you broke your actual conductor right here, well, then you'd be out of luck because then you wouldn't have a complete circuit. But still, one load going out is not going to affect the rest, right? The other thing that's interesting about parallel circuits is adding new loads or resistors in other pathways doesn't affect the resistance of any other pathway. So whatever goes on in this pathway, it's not going to affect this one. This one does not care. Okay. Now houses are wired this way with very good reason. Of course, you'd want your house wired as a parallel circuit. Imagine the alternative. The alternative was that your house was wired as a series circuit. As soon as one thing went bad in your house, like let's say one light bulb would burn out in your house, that would mean literally every appliance in your house would also go out of power. Could you imagine how annoying that would be? Because like your power would go out and you're like, oh, what was it? Which light bulb broke, right? Or did the fridge just like break, or like who knows, right? You wouldn't know. You'd have to like check literally everything. That would be extremely annoying. That wouldn't even be practical. So that's why houses, of course, are wired as parallel circuits, so that if one thing goes out, you still have your other things and you can immediately determine what went wrong. New Christmas lights, or at least the ones maybe that cost a little bit more money nowadays. I don't know. I don't buy Christmas lights very often. I just know the last time we ever bought Christmas lights, they weren't wired that way. But newer Christmas lights are wired as parallel circuits. So if your whole chain of Christmas lights, one of them goes dead, you still have the rest of your chain and you can immediately figure out which Christmas light you need to change. Okay, anyway, moving on. All right, so here's a thing I put together. There's an interactive app that I'm going to share with you guys on Monday. There'll be a bit of a project to it. I'll get to that later. But this shows a circuit that I put together, and hopefully you can identify what type of circuit this is based on the design. It is a parallel circuit because I've got parallel loads in different strands. But this yellow box here, it's hard to tell by the picture, but this yellow box right here shows a switch in the circuit. The switch right now is closed, and that's why these light bulbs are on and they're glowing, right? What would happen if I opened this switch? If I broke this switch open right now, what would happen to these light bulbs? Would either of them go out? Would only one of them go out? Would none of them go out? What do you think would happen? So here's what would happen, just to make it really clear. Remember, electricity wants to flow from the negative end to the positive end of a battery or a single cell as easily as it can, right? Now, here's the thing. If I opened this switch right now and broke this chain, the electricity can still make its way through this light bulb and back to the positive end of the battery, no problem, right? So this bulb is definitely going to stay on. It's good. This bulb, however, because the electricity can't go through here, it can't find a way to this light bulb unless it went down here and then over here and then to the light bulb. But then it's stuck because it can't go anywhere further. And electricity can't just literally just turn around. It doesn't work like that. It's like imagine if this was a pipe full of water. Like water wouldn't be able to go, oh, now I powered this, now I go right back down. It doesn't work that way, right? So if you open the switch, the correct answer would be this light bulb on the left would stay on, this light bulb on the right would go out. Anyway, moving on. So last thing we got to talk about today are microcircuits. You don't need to know too much about this, but basically in advanced electronics, normal circuits won't be practical. You can't have like a large circuit you can have in a microchip. It's not going to work that way, right? So that's where microcircuits come in. These are often called chips or microchips. Instead of a large physical switch to control electrical current flow, microcircuits use a silicon-based component called a transistor to control flow on a circuit board. These are built right in, they're right in with the circuit. But a transistor has different layers of silicon that will control current flow. And it's pretty complicated, so you don't need to know the great details about it. And these can be microscopically small, especially nowadays, but still really interesting that we can power such a complicated circuit board such as this. And if you really squint really closely on a circuit board, you can see all these lines. Those lines are where the currents are actually going, right? So in other words, that's like the conductor going through your whole circuit board. Anyway, we're going to move on from that. We don't need to know that too much. So for practice, I want you to do page 316, questions 1, 3 to 5, 7, and 11. It's a whole series of questions here, but really, really important. And some of them are going to get you to look at actually analyzing what different circuits would do. Really, really interesting stuff here. And just a heads up, on Monday next week, there's going to be an assignment where you will create a digital series circuit and a digital parallel circuit, and then submit a screenshot of each. Just so you know, this thing I put together is using that same app that I'm going to share with you on Monday. It's really cool to play around with. But be sure by the end of today that you have a good understanding of the difference between a series circuit and a parallel circuit, because I will be getting you guys to create a functional series circuit and a functional parallel circuit digitally next week. Anyway, as always, if you have any questions, please let me know. Best of luck on these questions, and I will talk to you on the Zoom.